Question 18, distinguish between an Arrhenius acid and a Bronsted-Lowry acid. Support your answer with two equations involving HNO2. So an Arrhenius acid, by the formal definition, all of the words that you want to include in your answer, is a substance that produces hydrogen ions. And then you can include extra detail in your answer. This is a chemistry exam, so anytime you can include chemical formulas or chemical equations, you include that. So it's a substance that produces hydrogen ions, H plus, in aqueous solution.
Yeah.
So aqueous solution state is something that you also include in a chemical formula. So what we might even do is maybe you don't want to put the formula here, and we might put the formula at the end, and what we'll do is we'll include states in it as well. So something like this.
Yeah.
And then they want you to write equations to support your answer. So we can do like definition, definition, then two equations afterwards. But then if you do that, your two sentences are going to be stuck together, and you're gonna have to label the equations to tell me if it's Arrhenius or Bronsted-Lowry. So in terms of exam structure, or in terms of answer structure, sorry, it might actually be better for you to give me the definition, then equation, then the next definition, then the equation. It doesn't affect your marks because it's only a 3-mark question. You don't get marked on structure, but good habits from the smaller mark questions. And also it's just easier for your marker to read.
Yeah.
So I might actually write the equation for the Arrhenius acid right now. And also it helps you link with this. And then it's really obvious, hey, marker, you can see the H plus. I've shown you that it's Arrhenius acid.
Yeah.
So HNO2, it's in aqueous solution, so it has to be AQ. And then with Arrhenius acids and bases, you don't talk about the degree to which it produces hydrogen ions. It's just, does it produce hydrogen ions at all? So we use a single arrow for anything that's an Arrhenius acid or base. And then if it produces the H plus, then the other thing that gets made is NO2 minus.
Yeah.
Okay, and then your Bronsted-Lowry acid is a substance that donates a proton to a Bronsted-Lowry base. So what that means is when you're writing the equation for the acid, you obviously need the acid in there, but it's not about what the acid makes, it's about what the acid does in relation to something else, which means your acid can't be the only thing on the left-hand side of your arrow. You need a base that's taking the proton from the acid as well. And then we know normally if it depends on what the equation is. It could be like an acid-base neutralization equation, but normally if the acid is in solution on its own, you write your dissociation equations with a plus water. That's what we usually do. So for your second equation, HNO2, now we don't get given enough information to be told if this is a weak Bronsted-Lowry acid or a strong Bronsted-Lowry acid. However, we can, so you can do a single arrow of this and you wouldn't lose marks for it, but hopefully you recognize HNO2 is actually a weak acid. And I think, what question did we do last time? It was question 12, where we talked about pH and there was HNO2 and HNO3 in there. We said HNO3 was strong, HNO2 is weak. So you won't lose marks if you don't know that because the question doesn't tell you it, but this is just good. We can make our answer as detailed as possible. So I know HNO2 is weak. I'm going to do a double arrow for that. And then it donates the proton to the H2O. So that's NO2 minus aqueous plus H3O plus aqueous.
Yeah.
Okay, and then that's all you need for this question. So it's either 1 mark per definition, and there are two definitions, and then it's like half a mark for each of the equations. That's probably the way it gets divided up. Otherwise, it's probably 1 mark per equation and then half a mark for each of the definitions. But that's very unlikely though, because they just tell you to use the equations to support your answer. Your equation is not your main answer. So the full
Yeah.
marks probably come from each definition, and then your equations are half mark each.
Yeah.
The other thing I'll say about this is that's all you need for a response like this. It's a 3-mark question. I know normally when you do Arrhenius and Bronsted-Lowry, from that part of the syllabus, you did the whole, oh, compare and contrast. What are the advantages? What are the disadvantages? Don't let your experience of a syllabus dot point affect how much you write. You don't want to waste time writing something that isn't going to end up giving you marks. So that kind of brain dump happens when you get a little bit anxious in an exam and you're like, I need to write a little bit more to see if I get the marks. But if what you're writing isn't relevant to the question, then it's not going to amount to any marks anyway.
Okay, yeah.
Yeah, so going into the exam, be very careful about what the question asks you for. Don't write something from memory just because it sounds like it's related. This question 18 is not asking you about which one's better or which one's worse. Distinguish just means to tell me the difference.
Yeah.
Question 19, explain why the pH of a solution of ammonia is greater than 7 degrees Celsius at 7 is greater than 7 at 25 degrees Celsius. Include one relevant chemical equation in your answer. Okay, so they're asking you to explain, which means I have to tell them why. Why is the pH of ammonia greater than 7? But for me to tell them why, I need to know what is even is in the first place. Like, what am I explaining? They're telling me to explain that pH is greater than 7, but I don't really know what pH is. I don't really understand what it means to be greater than 7. What does a pH greater than 7 mean? What is the question actually asking me?
Greater than 7 means it's basic.
Yeah, exactly. So what they're actually asking me is to explain why the pH of ammonia is basic. And something's basic due to the presence of
The hydroxide ions.
the hydroxide ion. Good. So I've broken this question down and now I understand what they're actually asking me to explain. They're asking me to explain why the pH is greater than 7, which is asking me to explain why ammonia is basic, which is basically saying, prove to me or tell me that ammonia makes a hydroxide in
Mm,
solution.
Okay, yeah.
So, question 19, ammonia is when it's in solution, the other chemical is the water. Water's amphiprotic, so it's going to be an acid or a base. So if we're writing an acid dissociation equation, you have acid plus water, which means water's the base. And then if you have a base dissociation equation, you have base plus water, which means water's the acid.
Yeah.
So water is whatever is the opposite of whatever the other thing is because the other thing is usually stronger. So if you get a
Okay.
stronger acid, then water's a weaker acid and it'll be the base. If you have a stronger base, water's the weaker base and it'll be the acid. So ammonia is a stronger base than the H2O it is dissolved in aqueous solution. And because of that, that's your explanation of why ammonia acts as a Bronsted-Lowry base. And what does a Bronsted-Lowry base do?
Accept the protons?
Yes, a Bronsted-Lowry base, it's going to take the proton from the water and that produces OH minus in aqueous solution.
Yeah.
So OH minus in aqueous solution means that the POH is going to be less than 7, and therefore pH is 14 minus POH is going to be greater than 7.
Yeah.
Solutions basic. And then they do tell you to include a relevant chemical equation. So that's where your 3rd mark comes from. Because at the moment, this explanation here kind of looks like it's just one explanation is normally 2 marks. So I'm wondering where my 3rd mark comes from, and that's from the equation. So what's the formula for ammonia?
NH3. aqueous.
NH3, aqueous, yes, good. And then I'm going to react it with water because that's what we said it's doing. And ammonia is strong or weak?
Weak.
Ammonia is weak, so it's going to be a double arrow. It takes a proton, so that turns it into NH4 plus aqueous plus OH minus aqueous.
Yeah.
Okay, good. Any questions?
No.
All right. Question 20. Calculate the percentage ionization of two acids given their Ka values. Do you remember what the equation for percentage ionization is?
It was the concentration of H plus on the like the acid.
Yes, good. The concentration of the H plus is at equilibrium because there's no H plus at the very start. Because assuming at time zero, none of your acid or base has dissociated yet, and then you're taking the total amount of acid at the start, right before it starts associating, so that's initial, and then times 100. And then for a base, instead of H plus up the top, what do you have instead?
OH minus.
Yeah, you have OH minus. So this is the ionization equation for a base. So your percentage ionization equation has some initial values in it, some equilibrium values in it, which means
An ice table.
I have to set up an ice table. Good. Okay. Now, if I have to set up an ice table, I need to know the equilibrium expression. If I know the equilibrium expression, I need the chemical equation. And then the chemical equation depends on what the reaction is. They either have to tell you the reaction or the subscript underneath the letter K tells you what the reaction is. So Ka means that it's an acid dissociation equation.
Mm,
Ethanoic acid is easy enough. They don't have to give you the formula because you know it from module 7.
yeah.
Formic acid is actually a common name. It's not an IUPAC name, though. Do you know what formic acid is?
No.
Formic acid is methanoic acid. So in the exam, they would, if they choose to say formic acid, they'd have to tell you the formula. Otherwise, they should be using IUPAC names so that you can figure out the formula yourself.
Okay, yeah.
So first off, methanoic acid. What's the formula for methanoic acid?
CH um
Let's draw it out together. Formic acid, methanoic acid. How would we draw that?
one C's and then that's double that has a O like a double bond to O and then OH
Mm-hmm.
and then one hydrogen.
One hydrogen. Good. So the formula HCOOH, and that's aqueous. Acid dissociation equations, acid plus
Water,
water. And the fact that they've given you a Ka value means that it's a weak acid in the first place. So what kind of arrow am I using?
a double arrow.
A double arrow. This is an acid dissociation equation. So the HCOOH is losing a proton. What do I make on the right-hand side?
COOH minus plus H3O plus.
Yes. The OH at the end is the hydroxyl functional group in the carboxyl. So this is actually the hydrogen that pops off. So this is the acidic hydrogen, not this one here. The carbon hydrogen bond is non-polar, so it doesn't feel the need to pop off. Oxygen is electronegative, so it's more likely to steal the electrons from hydrogen. That's the hydrogen that pops off. So when I do that, I'll actually leave the first hydrogen. I'll keep the H and then I'll get rid of the second one.
Yeah.
Okay, so we need to set up an ice table ICE. And the initial concentration of the acid they've given me, 0.010. The water I don't have to worry about because it's a pure liquid. And then I don't get told about any of the products initially, which means I assume it's
0.
0. And if it's 0 at the start, according to Le Chatelier's principle, I will be shifting to the
Right.
right. So plus x, and therefore for the left, it's going to be
Minus X.
minus x. So then this is 0.010 minus x, this is x, and this is x. And then for me to solve for x, I need the Ka value, which they've given me, and then I need the equilibrium expression, so I can sub all of these x's in. So what is the equilibrium expression?
HCOO minus and then H3O plus on HCOOH.
Yeah. COOH, and then this is X and X on 0.010 minus X, which is X squared on 0.010 minus X, and that's equal to the Ka they gave me, which is 1.8 times 10 to the minus 4. Now, if I were to solve this the way it was, I would have to be solving a quadratic, and I need to use minus b plus or minus b squared, da 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 da. How can I make a simplifying assumption so that I don't have to solve the quadratic?
Assume that X is way, way smaller than 0.01.
Yes, good. So I'm going to say Ka is very small. If Ka is very small, then the x's that go into solving for Ka is going to be very small as well. So then assume X is way smaller than 0.010. So therefore, this is just a so therefore, actually, before I even sub it back in, X is way smaller than 0.010. So 0.010 minus X is approximately just 0.010.
Yeah.
Then I'll put it back in the fraction. So this is approximately X squared on 0.010, 1.8 times 10 to the minus 4. And then how do I solve for X?
Multiply both sides by 0.010 and then square root that.
Yes. Okay, and then what do we get for X?
That's 1.34 times 10 to the minus 3.
Times 10 to the minus 3. And then that's molarity, because that's something I get from my ice table. My ice table takes concentration, molar concentration. And then I don't actually know what X is, because X is just a letter. So going back to the question, I actually want the hydrogen or hydronium ion concentration at equilibrium. So I'm going to go back to my ice table. What is the hydronium ion concentration in terms of X?
It'll be the 1.34 times.
Yes, good. Because I look at the H3O plus and I see that it's exactly equal to X. So I don't have to do 0.01 minus X or anything like that. If they were asking me for acid at equilibrium, then I would have to do that. So
Mm.
H3O plus at equilibrium is equal to X is equal to 1.34 times 10 to the minus 3. And then my job now is to just sub it into the formula that I had earlier.
Yeah.
So H plus or H3O plus at equilibrium over HA initial times 100 is my 1.34 times 10 to the minus 3 over the acid at the start, 0.010 times 100. What is our percentage ionization?
13.4%.
13.4%. My concentration that's given to me, it's 2 sig figs, and my
Uh,
Ka is also 2 sig figs, so I'll round this off to 2 sig figs as well, so that's just 13% to 2 sig figs.
okay, yeah.
All right, any questions?
Mm,
Do the same thing with B, just with a different acid. So B is ethanoic acid. What's the formula for ethanoic acid?
C2H 4O.
Let's draw it out. How do we draw ethanoic acid?
Two C's.
Mm-hmm.
And then double bonded to OH.
Double bonded to O, OH.
And then fill in the rest with hydrogen.
Mm-hmm. Okay, so what's my formula?
That's C2H4O.
O2, because there's an oxygen here and there's an oxygen here as well. With organic chemicals, we like to do it in terms of condensed formula, just so you can still see the structure. So an alternative way of writing this formula is CH3COOH, which is the way you normally see it, like with acetic acid in your exam questions, just because it gives you a better idea of the structure.
Yeah.
And so we might do that actually. The reason being is because it'll make it easier for you to see which hydrogen to take off.
Yeah.
So CH3COH aqueous plus H2O, double arrow again. They've given you the Ka, so you know it's weak, but also we know ethanoic acid is weak. And also any carboxylic acids from module 7 are weak.
Yeah.
Plus H3O plus aqueous. Set up your ice table once again. And the initial concentration of the acid, 0.1 molar. Don't have to worry about the water. My products are 0 and 0. I'm shifting to the right. It's a 1-to-1 ratio. So plus x and minus x. So 0.10 minus x with x and x. Sub it into my equilibrium expression again. What is my equilibrium expression?
CH3COO minus H and then H3O plus on CH3COOH.
Then I'm going to sub my answers in. That's x and x on 0.10 actually this time. 0.10 minus x is equal to the Ka they've given me, which in this question is 1.8 times 10 to the minus 5. Assuming again, Ka very small. So therefore, x is way smaller than 0.10. So this is approximately just x squared on 0.10 is equal to 1.8 times 10 to the minus 5. And then how do I solve for x?
Times both sides by 0.10 and then square root that.
Yes, 1.8 times 10 to the minus 5. And then I'll square root it. That will get rid of my squared. And then what do I get for this?
1.34 times 10 to the minus 3.
1.34 times 10 to the minus 3. X is from your ice table, which takes concentration. So this is molar. And then we don't want X, we want the equilibrium concentration of H3O plus. So I look at H3O plus, I go down to the E row for equilibrium, and I realize that is exactly equal to X. Now I've got everything I need. I don't need the acid concentration because my equation for percentage ionization takes initial concentration, which they already gave me in the question. So I sub that straight in, H0 plus EQ on HA initial is equal to 1.34 times 10 to the minus 3. The initial concentration of the acid, 0.10 molar, and then I times by 100.
And then that's 1 point or like 1%.
1%.
Yeah.
So we're rounding to 2 sig figs, so that's 1.0% to 2 sig figs.
Oh, okay, yeah.
Okay, good. Any questions?
No.
Uh, Delete. Question 22, prove the equation KAKB is equal to KW. This is from the notes exactly. So I think we did prove it together. Proving the equation KAKB is equal to KW. Few different ways of doing this. When you add equations together, it multiplies the K values. So when it says, oh, Ka times Kb is equal to Kw, that kind of looks like if you add the equations for Ka and Kb, you'll multiply them together, and that'll equal to your Kw equation.
Yeah.
So let's see if that's true. So your equation for Kw is 2H2O liquid turns into H3O plus aqueous plus OH minus aqueous. And then you can tell the marker, this is Kw.
Yeah.
And then for an acid, we'll go HA aqueous plus H2O liquid turns into A minus aqueous plus H3O plus aqueous, and that's Ka.
Yeah.
And then you have, now Ka and Kb is for conjugate acids and bases. So normally when you're writing your dissociation equations, we do HA for the acid and then we do B for the base.
Yeah.
Can't do that in this case because then it kind of looks like you have two completely different chemicals. Ka and Kb only works for conjugate acid-base pairs. So if this is the acid, when I go to write my Kb equation, I'm actually going to take this as my base.
Okay, yeah.
I can't take a random letter B because then they would no longer be conjugate acid-base pairs.
Okay, yeah.
So for the Kb equation, I'm going to take the conjugate base of the HA, which is A minus, plus H2O turns into, it takes a proton this time, so then it turns back into the conjugate acid
Yeah.
plus an OH minus.
Yeah.
And then this is Kb. And then we said in the equation, they were trying to get you to prove Ka, Kb is equal to Kw. From what we know, actually in the Module 5 recording that we went through, when you add equations together, you multiply the K values. So if we're trying to show Ka times Kb, then we have to be adding the equations together. And hopefully that gives us the equation for Kw.
Yeah.
So let's add this together. Anything on opposite sides cancel out. What do you see on opposite sides?
The HA and the A minus.
Yes, the HA and the A minus, and anything on the same side adds together. What do I have left over on the left-hand side of my arrow?
2 H2O.
Yeah, two of the H2Os, and then what do I have left over on the right?
H3O plus and then OH minus.
Yes. So then when you add equations together, the K value of this is going to be Ka, Kb.
Oh, okay, yeah.
And then I realize equation 1 and equation 2 are the same.
Yeah.
So therefore the K values must equate because it's the same equation.
Yeah.
And then that's how you get Kw is equal to Ka, Kb.
Yeah.
Okay. Any questions?
Mm,
23A, calculate the hydroxide ion concentration of an aqueous solution with a pH of 11.7. Hydroxide is OH, so I don't want to be working with pH. I want to be working
OH.
with POH. So for part A, POH is equal to,
10 to the minus P. Oh no, sorry, that's negative log of OH minus.
yep. And then where am I going to put my pH in? POH is equal to
14 minus POH. Oh,
POH
minus pH.
minus pH is equal to 14 minus 11.7, which gives me
2.3.
2.3. And then I can sub that back into this equation up here. So then rearranging this, what's the hydroxide concentration equal to?
10 to the minus 2.3.
10 to the minus 2.3, which is equal to
5 times 10 to the minus 3.
5 times 10 to the minus 3. How many sig figs do I want to round off to?
4.
Okay, so my answer is 5
Point 012
1,
times.
2 times 10 to the minus 3. And then this is hydroxide concentration, so that's going to be units of molarity as well.
Yeah.
Okay, and then part B, what assumption did you make in part A? The pH plus POH equation turning equal to 14 only works at what temperature?
25 degrees.
Good. So the assumption I'm making is that everything's happening at 25 degrees Celsius.
Okay, yeah.
All right. And 24, A 49.9 gram sample of barium hydroxide octahydrate is dissolved in water and the solution is diluted to 2.5 liters. What is the concentration of hydrogen ions in the solution? Okay, I've got a barium hydroxide, which means it's a base. So I'm used to finding hydroxide concentration first, which means I have to convert to hydrogen ions after.
Yeah.
It's a base, I work with hydroxides, then I'll figure out a way to get to hydrogen ions. So they want concentration, assuming molar concentration, C is equal to N on V. So that I need the moles, and then I already have the volume. I have mass. I need to turn this into moles. So I'm going to do mass on molar mass. For molar mass, I need to know the chemical formula. So moles, what's the formula for barium hydroxide?
BaOH2.
BaOH2, and then octahydrate. Hydrate means water, octa means
8.
8. So dot 8 H2O. So there's 8 water molecules as ligands. So that goes into my molar mass calculation. So mass on molar mass is 49.9 grams. What's the molar mass for barium?
I don't have my periodic table.
Let's have a look for it. Barium is 137.3. How many hydrogens do we have?
There's 2.
There's 2 here. How many hydrogens do we have in total?
That's 2 plus 16, so 18.
18. So 18 times 1.08 for hydrogen. How many oxygens do we have?
9.
9. The
Sorry.
2 on the
That's 10.
10 times 16 for oxygen grams per mole. How many moles of barium hydroxide octahydrate do we have?
That's 0.018, so on.
0.018, so on. And then now that we've got moles, I've got moles of the entire chemical, but with bases, I want to work with just the hydroxide. I'm going to convert from hydroxide ions to hydrogen ions. I can't convert from the entire molecule to hydrogen ions. So how many OHs do we see in the formula?
There's 2.
There's 2. So when I get the moles of the entire chemical, I'm going to times it by 2 to get all of the moles of the hydroxide. So that's 2 times the moles of barium hydroxide octahydrate. 2 times 0.018 dot 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 mole is equal to
0.037, and then
0.037 dot dot dot. Now that I've got the moles of hydroxide, my equation, now I normally do pH and pOH calculations, and then I'll go to hydrogen or hydroxide ion concentrations after. But this question doesn't require me to use pH or pOH at all. So I don't really want to have to convert to pOH, convert to pH, and then convert to hydrogen ion concentration. There is an alternative equation that bypasses the pH calculation, which is H3O plus OH minus is equal to 1 times 10 to the minus 14.
yeah.
So from here, I know I need to get to hydroxide ion concentration. So OH minus is equal to moles on volume, 0.037 dot 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 mole divided by, what's the volume?
2.5.
2.5 liters. So what's my concentration of hydroxide?
0.015.
0.015 dot 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 molar. And then I have this formula that I can use to get to proton concentration, which is what they're asking me for. So my final answer, H3O plus, is rearranging this, the 1 times 10 to the minus 14, and I divide my OH minus.
Yeah.
So 1 times 10 to the minus 14 divided by 0.015. What is my hydrogen ion concentration?
6.64 times 10 to the minus 13.
Times 10 to the minus 13. Thank you. And my final answer, I round off to 3 sig figs. So that's that.
Okay, yeah.
Any questions?
No.
So you can find this section on the OneNote when we upload it. Question 26 we did last lesson, so go look at the lesson recording for that. Question 27, a 10 ml sample of nitric acid is transferred into a 100 ml volumetric flask. 25 ml of the diluted acid is transferred into a conical flask and then titrated with 0.15 molar NaOH. If the average titer of NaOH is 23.33, what is the concentration of nitric acid? Is this a direct titration, double direct, or a back titration? I need to know because it affects how I do my working out. It's a direct titration because there's only one acid and there's only one base, which means you can only do one acid-base reaction with it. Double direct and back titrations both have 2 reactions. So because there's only one reaction in 27, I know it's a direct titration question. Direct titration questions I can treat as a stoichiometry question pretty much because they've given you information for one chemical, the NaOH, and then they're asking you for the nitric acid. So when you treat it like a stoichiometry question, they've given you NaOH, they're asking you for the acid, I need a chemical equation, and I read the equation in terms of moles. So that's step 1. What's the formula for nitric acid? You saw it earlier today. HNO3, and then NaOH they've given you. Acid plus base turns into salt plus water. What's the salt that gets formed? What's the formula of the salt, please? Sodium nitrate, NaNO3. Good. And then water gets formed. They're asking me for the nitric acid, so that's where I want to end up once I'm done using my equation, which means I start at the NaOH. And then once again, like any stoichiometry question, I read my equation in terms of moles. So if I'm going to start at NaOH and I want to end up at HNO3, I need to read the equation in terms of moles. I need to get the moles of NaOH. They've given me concentration. They've given me titer, which is volume from the burette. So I do C times V, which is 0.15 molar times 0.02333 liters. What do I get for the moles of NaOH, please? Point 0.00349995, thank you. And once I've got the moles of the chemical, I can jump to the moles of the other chemical. Reading my equation, I was supposed to balance the equation at the start. We didn't. It's a 1-to-1 ratio, so it's fine. So what's the moles of HNO3 going to be? The same, so moles of HNO3 is going to be 0.0034995. Now, I just used my chemical equation to get the moles of HNO3, which means at the moment, I'm in the context of the conical flask. This is the moles of HNO3 in the conical flask where the reaction is happening. When they ask you for what's the concentration of nitric acid, they should have also specified what's the concentration of nitric acid in the original solution, which means where it originally came from. Okay, where it came from. This is where it came from. It came from a 10 ml sample. The issue is I'm not in the context of the 10 ml sample. I'm in the context of the conical flask. If the 10 ml sample got put into the conical flask, great, but that's not the case here. What volume actually went into the conical flask to do the titration? The 25 mils, good. Read the question here. 25 mils of the diluted acid is transferred into the conical flask. So when I go to calculate the moles of HNO3, that's in the conical flask. That's where the reaction is happening. That's in a 25 mil sample. So I have to go back up, work my way backwards to get to the original sample. Can I jump from 25 back up to 10 now? Is that how it happened at the start? Did they go 10 to 25? Because if they went 10 to 25, when I work backwards, I can just go straight to the 10. Is there any volume in between that? There's a 100 in between that. Good. So they didn't dilute 10 straight into 25. They didn't go 10 mils and then add 15 mils of water. What they did was they went from 10, they diluted it to a 100 mils flask, and then from 100 mils, they only took 25 mils. So from 10 to 100, they diluted it, and then from 100 to 25, they just took out 25 mils. So when I work backwards, I need to just reverse their process. So they went 10 to 100 to 25. I'm currently at 25. I'm trying to go back to 100. When they went from 100 to 25, did that change the moles? No? Yes, it did. Good. So it changed. No, it didn't change concentration. Concentration changes when you dilute something, which is when you add water to it, or when you put in more moles, or like when you take out moles. The issue is though, what's the final step when you're making a solution in a volumetric flask, guys? You invert it, and then what's the word starting the H? You put a flask on, you invert it, so that what can you do to the solution starting the H? You homogenize the solution. Good. If you remember, when you make a standard solution is something you made in year 11. Sometimes they let you do it again in year 12, right before you do the titration. Give me a thumbs up if you did that, or if your teacher just made you start the titration straight away. Yeah, some of you guys did it again. Yeah. So once you're done making your primary standard solution that goes into your titration, you put the stop cork on, you invert it, and then you like do that squiggly thing to try to homogenize the solution. Homogenizing the solution means that the concentration is the same throughout, which means if you have like 100 moles in it and then you divide the volume up by 10, it should be perfectly divided. So if you have 100 moles and you divide it up by 10, then each volume should each have 10 moles because you've perfectly distributed the moles in the system, which means that when, in this case, they didn't divide by 10, they went from 100 to 25, they divided it by 4, the moles should also perfectly divide by that amount. So the only time you change concentration, so guys, the only time you change concentration is when you change moles without changing the volume, or you change the volume without changing the moles. Because then you don't, C is equal to N on V. If you change one without changing the other, then you mess up the ratio of N on V, and that's when you change concentration. But when they went from 100 to 25, they divided the volume by 4, which means the moles also divides by 4. So because you've implemented the same change throughout, concentration actually stays the same. So from 100 to 25, they divided the volume and the moles by 4, which means, guys, when I work backwards, I'm at 25, I'm trying to go to 100. What do I have to do? I have to times by 4. Good, I'm tracing my steps back. So times by 4. What happens, how many moles do I get in the 100 mils then if I times by 4? 0.0, 0.013998 mole. Thank you. And then that's not it. I'm at 100. There's one more to go. 100 to 10. So they went 10 to 100. I'm going back from 100 to 10. From 10 to 100, they diluted the sample. Diluting the sample means you add more water to it, which means they changed volume, guys. So then what we were saying earlier, they changed volume, but they didn't change moles. When you change one without changing the other, that's when you affect concentration. So the 10 mil and the 100 mils, they have different volumes, but the moles stayed the same. When you have a 10 mil sample, and let's say you have a certain number of moles in there, all you did was pour some extra water into it. So the height went up, but the moles stayed the same. It's just that they're a bit more they're more dispersed in the bigger volume. So that's like trying to dissolve salt in water, and then you're like, oh, all of the salt isn't dissolving. I'm going to pour a bit more water into it and then keep stirring it around. You didn't put more salt into it. You kept the same amount of salt. You just added more water in. So from 10 to 100, all they did was add water. They didn't change the moles, which means when I go from 100 back to 10, I don't change the moles either. This is 0.013998 moles in the 10 mils. Now that I'm back in the context of the original 10 mil solution, I can go to calculate the concentration of that solution, which is straightforward. N on V is equal to 0.013998 divided by 10 mils, which is 0.010 liters. What do we get for concentration then? 1.3998. How many sig figs do I want to round off to? 2. So my final answer is going to be 1.4 mole to 2 sig figs. Okay. Take a second to grab that down. How do you know it's diluted to 100 and not something else? Because it was just transferred to a 100 ml flask. That's a good point. You can call it an assumption. It's sort of not an assumption though. A volumetric flask only has one line. So it's not like a measuring cylinder. If they said, oh, they transferred 10 mils into a measuring cylinder, then I'd be like, okay, so did they add the water to make it 20 or 30 or 40 or 50? With a volumetric flask, if you remember when you did it in class, there is only one line at the correct volume that it's measured at. So when they tell you that they transferred it to a 100 mil flask, yeah, technically speaking, they didn't say they added water so that it went to 100 mils, but that's the assumption that you have to make. Otherwise, you really won't know what volume it goes into. Let me know if that makes sense. There's only one line in a flask. So if it's not in 100 mils, then you can't answer the question. So they would have had to word the question differently. Yeah. Also, would the 10 mil and 100 mil indicate one sig fig if we somewhat used it? It's arguable. With that one, sometimes people if the 0 is before the decimal place, some people argue it differently. So if you search it up online, people will say you can either count that as 1, 2, or 3. So it's really up to you. And then the more sig figs it is, the better it is in terms of writing your answer. So I tend to go the more sig fig way. Now, the reason it's ambiguous is because, like, let's say you have something like, let's say, imagine you're rounding it off, yeah, and you're not the one that sees the 10 mil or 100 mils. Let's say you do a working out, and then your answer is 121. Okay, let's say your answer is 121. Let's say your answer is like, yeah, let's say your answer is like 121, and then whatever answer you get, it's like 121, and then you're going to check the numbers in your question, and you're like, oh, I have to round it off to 2 sig figs, in which case then it goes down to 120 mils. But then you kept the digit afterwards in there, which means you can count it as as 2 sig figs or as 3 sig figs. So when you have the 0 before the decimal place, it's arguable. People online will say 1, 2, or 3, but it's completely up to you. There's no saying if you count it as 1 or not. Yeah. Whether or not something's significant depends on whether it changes your answer or not. If you were to count it as not significant, then it kind of looks like the answer is just 1. So it's a bit ambiguous because the zeros afterwards, they don't really do anything. But if you don't count it as significant, then it kind of looks like you only have 1 digit. That's why with the ones where there are zeros and there are no decimal places, it looks a bit funny. Now, we're not nitpicky in the HSC for it. There is a technical answer, and the technical answer is this. If it's 100, the technical answer is this. If it's 100, then it's 1 sig fig. But if it's 100 with a dot, then it's 3 sig figs because there's a decimal place involved. Yeah. We don't bother with this though. And also your calculator doesn't do this. Your calculator doesn't give you a dot without anything afterwards. That's why it's also ambiguous. But this is the proper way of counting it. If there's a really technical answer that you find online, this is the technical answer. But for us, if it's 100, then we tend to do 1, 2, or 3 sig figs. Question 28. A 10-gram sample of impure magnesium is reacted with 300 ml of 2 molar HCl. The solution is diluted to a 1 liter flask. 100 ml of the diluted solution require 33 ml of 1 molar NaOH to neutralize it. What is the percentage purity of magnesium in the sample? Direct, double direct, or back titration? Three, two, one. It's definitely not what? Which one can you immediately cancel out of the 3? It's definitely not a direct titration because there's 2 reactions happening, the magnesium with the HCl and then the HCl with the NaOH. So it's definitely not a direct titration. It's going to be a back titration. Good. Oh, sorry, James. It's going to be a back titration. Now, you're looking for words like excess if it's a back titration, but you don't see that word here, which might be why you're thinking it's a double direct titration. Okay. The other thing to keep in mind is this. If it's a back titration, a double direct titration, it's in the name, it's a double titration. A double direct and a back titration both have 2 reactions. That's why you cancel out the direct. The difference between a double direct and a back is that a double direct titration has 2 titrations in it. The point of a titration is to figure out a concentration each time, which means that when you read the question, there should be 2 concentrations that you're looking for, 1 in each reaction. So in question 28, we know that there's 2 reactions. There's Mg plus HCl, and then there's the HCl plus the NaOH. You should be looking for a concentration each time. In the 28, they told you it's 2 molar HCl. So the magnesium is what you're looking for. And then the HCl and NaOH after that, the concentration of HCl is already given to you. You know it. And they also know the concentration of the NaOH. So the only thing you're looking for is the magnesium. 2 reactions, but only 1 concentration to find. That's a back titration. The other way of thinking about it is that with a back titration, because it's only 1 titration, even if you don't see the word excess, with one of the reactions, you should not be seeing titration terminology. Yeah. If it's a double direct titration, you should be seeing titration terminology with both reactions. You should be seeing titer, you should be seeing aliquot, you should be seeing standardized, you should be seeing the word titrate, literally. If you only see that for one, then it's a back titration. Notice the wording for the first sentence. The 10-gram sample is reacted with. It doesn't say titrated against. And then only after that does it say, oh, required 33 mils of NaOH to neutralize with it in a volumetric flask. Okay, give me a thumbs up, guys. Does that make sense? Double direct, two titrations. One titration means one concentration. So if it's two concentrations, it's double direct. But if you see two reactions, but you only figure out one concentration, every other concentration is known, that's a back titration. So with a back titration, you need to start with the second reaction first. You know the moles of HCl that you add to the first reaction, but it's added in excess. So that's not the amount that actually reacts with the magnesium. So you're looking for moles of HCl added in the first reaction. Be careful about using the word added, because that's not the same thing as titrated, or that's not the same thing as reacted, because it's added in excess. So the amount of HCl that you added with the magnesium at the start, it was a 2 molar concentration, and it was 300 mils. That doesn't mean all 300 mils reacted. It's added in excess. So C times V, 2 molar times 0.3 liters. You guys don't need to pop this in the calculator. It's 0.6 moles. Hopefully I got that right. That would be embarrassing. So you added 0.6 moles in total. We can't go to the magnesium yet. I know we said that when you're reading an equation, you can get the moles and you can jump to the other chemical, but that's only if the moles you calculated is the moles that's actually reacted for the equation. This is the moles that goes in, but we don't know the moles that reacted. I can't know the moles that reacted. What I can know is the moles that's left over that gets titrated later on. So I have to calculate that first. The moles of HCl titrated with NaOH is a thing I get after. That's what I'm looking for. But for me to know the moles that got titrated with NaOH, I need to now go in the context of my second reaction. HCl with NaOH turns into NaCl plus H2O. For me to know the moles of HCl that got titrated, I need to know the moles of NaOH that got titrated with it. Moles of NaOH, C times V, 1 molar and 33 mils. 1.0 molar times 33 mils, 0.033 liters gives me 0.033 moles. So that's the moles of NaOH that titrated with the leftover HCl. So what's the moles of the leftover HCl, guys? Based on the equation that we've written. If that's the moles of NaOH in the titration, what's the moles of HCl in the titration? It's the same because it's a 1-to-1 ratio. Now here's the thing though, the amount of HCl that went into the titration, is that all that was left over after the first reaction? Can you read the question carefully? The amount of HCl that they put into the titration, is that everything that was left over after the first reaction with magnesium? What volume went into the titration with NaOH? Let's start there. Break the question down with me. Walk through it together. What volume reacted with NaOH? 100. So like the volume doesn't even match, okay? The volume that they reacted with the magnesium was 300, but then they only 100 went into the titration or went into the reaction with NaOH. So that doesn't even match to begin with. Yeah, that's not the end though. So when you look at that, you're like, hey, the volumes don't match. Did they divide by 3? They went from 100 and then they divided by 3 to get to 100. Is that the case? Did they go from 100, from 300 to 100? Is there any volume in between? What's the volume in between? 1 liter. Okay, so this is a back titration question with a volume change in the middle of it. So one more time, I know the moles of HCl that I added at the very, very beginning. Just because I added it doesn't mean I reacted all of it. But for me to know how much got reacted, I actually need to know how much is left over that didn't get reacted. Okay, so when I do that, I realize, hey, there's 0.033 moles left over that didn't react after my first reaction. But the issue is the 0.033 moles left over, that's in a 100 ml sample. The original amount of HCl that I put in, that wasn't a 100 ml sample, that was a 300 ml sample. So they must have done something in between the first reaction and the titration at the end. So this is 0.033 moles in 100 mils. It didn't go from 300 to 100. There's something in between. They went from 300 to 1 liter. And then from that 1 liter is how I got to my 100 mils after. So I'm going to work backwards, yeah? For me to work backwards, I need to know what they did first. How did they go from 1 liter to 100? What did they do? Did they dilute? Did they times? Did they divide or split the solution up? Because I'm going to reverse that. They divided by 10. So when they went from 1 liter to 100, the 100 is what they took for the titration. When they did that, they divided it by 10. So if I'm at the titration and I'm trying to go backwards, I'm timesing by 10. So therefore, times 10 is 0.33 moles in 1,000 mils, which is 1 liter. And then I'm not yet back at my first reaction. I need to know the total amount that was left over after the first reaction where I added it in excess. So I'm still not there yet. I'm at 1 liter. I'm trying to go back to 300. How did they go from 300 to 1 liter in the first place? How did they go from 300 to 1 liter in the first? They diluted it. Does that change my moles? No, when you're diluting, you're adding water, you're not changing the moles. So from 300 to 1 liter, they added water, they didn't change the moles, which means when I go back, I'm not going to change the moles either. I'm just reversing their steps. So this is the same 0.33 moles in the 300 ml sample at the very start. Okay, so I'm now back at the same context. Guys, you can't add or subtract numbers together unless you're in the same context. The moles of HCl in the first reaction, that was 0.6 moles in 300 mils. Now I've figured out that there's leftover 0.3 moles in the 300 mils. So the moles of HCl that got titrated with NaOH is 0.33 moles in 300 mils. So I know the moles that got added. I know the moles that got titrated. How do I get the moles that got reacted in my first reaction? I know the moles added. I know the moles left over. So the moles reacted is the amount added minus left over in titration. Good. Which is equal to the amount that I added is 0.6 moles. The amount that was left over that went into my titration is 0.33 moles. So how many moles did I lose in my first reaction? Point 0.27. So 0.27 moles of HCl got lost in its reaction with Mg. 0.27 moles of HCl got lost in the reaction with Mg. One more time, I couldn't take the 0.6 moles at the start because that wasn't the actual amount that reacted with Mg. That was just the amount that got added with Mg. Not all 0.6 moles reacted. Now I know only 0.27 moles of that actually reacted. Once I know the amount that actually reacts, I can now use the equation for the chemical reaction. Just because you mix things together does not mean you react it. Remember, there's a limiting reagent and there's an excess reagent. So now that I'm in the reaction with Mg, I can write the equation for it. Who remembers the metal plus acid reaction from year 11? What does this turn into? The reason this is still part of the course is because this is something you did in module 6, yeah? So it seems like a year 11 reaction. You did acid base, you did acid carbonate, but you also did acid metal at the very beginning of module 6. Hydrogen gas and salt, good. So the salt is magnesium chloride, MgCl2, and then H2. How do I balance this equation? 2 on the HCl. So I've got my moles of HCl, 0.27. I can go to my magnesium now. How am I going to get my magnesium from my HCl based on our balancing? Times a half, good. So what's my moles of magnesium going to be? Yes, 0.135 mole. Now that I've got the correct chemical that they're after, I can see what they're after. Of magnesium, they're actually after percentage purity. Percentage purity is how much of the entire sample actually contains magnesium. With percentages, you tend to do it in the same units. So the whole sample is 10 grams. So if they want percentage purity, I can't do moles as a percentage of grams. I have to do grams as a percentage of grams, which means I'm going to take the moles of magnesium and I'm going to figure out how many grams that is. And then I'll put it over the whole 10 grams to see what it is as a percentage. So that's the moles of magnesium. Mass of magnesium is going to be moles times molar mass, 0.135. Molar mass of magnesium, 24.31. Confirm for me if that's correct, 24.31. 24.30, 24.31 grams per mole. Thanks, Cody. So moles cancels out. What do we get for grams? Three 3.28185 grams, thank you. And then percentage is, it's a percentage of 10 grams. So percentage weight on weight of magnesium. Weight on weight is mass over mass. So 3.28185 grams over 10 grams times 100. 32.8%. Okay. So guys, your key learning from this question, I know this was worded a little bit different. It actually does not look like your regular titration question. You have to look at it a few different ways. So first things first, when you notice an acid-base question, step one, identify how many reactions there are. Divided by 10 grams because the question was asking me for percentage purity. Percentage purity means what is it as a percentage of the whole thing that it was in. And magnesium, they said, was in a 10-gram sample. So that's why I divided it by 10. Step number one, that's all good. Step number one, when you see a titration question, read it to see if you can only write one equation, if you can write two. If you can only write one, it is a direct titration. If you can write two, then you have to figure out if it's double direct or back titration. This question was kind of difficult to figure out because it doesn't have the usual signs that we're after. Okay, you normally look for the word excess. If it's excess, it's easily a back titration question. If you see titrate or titer or aliquot for only one reaction, that's easily a back titration question. The reason this was difficult was because the second reaction with the NaOH didn't use any titration terminology at all. So that's where it became extra confusing. So because you didn't see extra titration terminology, you might have thought both of them were regular. You might have thought both of them were the same thing, in which case, if they didn't use titration terminology for both, or for only one, that must mean both of them are titrations, yeah? If you don't see titration terminology, that does not immediately mean that they're both titrations and not just one of them. Your last resort is to figure out how many things you're looking for the concentration of. There's three chemicals here, magnesium, HCl, and NaOH. For two of the three, you know the concentrations, which means there's only one that you don't know the concentration. That has to be a back titration. This is your last resort. If it's a double direct titration, you're looking for two concentrations. If you only are missing one, then it's a back titration. Can I get a thumbs up, guys? Does that make sense? This is your last resort, yeah? The chances that you see something like this, I don't know. Question 28 is more of a trial question. With the HSC, they'll be complex in different ways, but this is your last resort for identifying the different things, yeah? Question 29, a chemist wants to determine the percentage by mass of calcium carbonate in a sample of marble. A 0.188 gram sample of marble is dissolved in 27.2 mils of 0.2 molar HCl. Excess acid required 23.8 mils of 0.1 molar NaOH to be neutralized. What's the percentage of calcium carbonate in the marble? This one has the signs that you're used to. Is this direct, double direct, or back titration? This is a back titration because it has the word excess that you're used to. Okay, so with a back titration, you figure out the moles added, the moles titrated, then you can figure out the moles that got lost in the first reaction. So the chemical that's being added in excess, that's going into the titration as well, is the HCl. So moles of HCl added at the start is C times V, 0.2 molar times 0.0272 liters. How many moles of HCl did we add? Question 29 is easier as well because there's no volume change in the middle. All of the acid left over goes into the titration. 28 should be worth more marks. Point 0.00544 moles, thank you. And then moles of HCl titrated depends on the moles of NaOH that it titrated with. So HCl plus NaOH turns into NaCl plus H2O. Moles of NaOH titrated is C times V, 0.1 molar times 0.0238 liters. That one's easy, 0.00238 moles. So therefore, it's a 1-to-1 ratio, just like the previous question. Moles of HCl is going to be moles of HCl titrated is going to be moles of NaOH is going to be 0.00238 moles. This question's easier than question 28 because once you've got the moles of HCl titrated, they don't mention any volume changes, which means this amount is in the same volume that this amount was. So I don't have to do any volume changes here. So I can go ahead and start my subtraction straight away. Moles of HCl reacted with my original sample. The original sample contained my calcium carbonate. Calcium carbonate is added minus titrated, 0.00544 minus 0.00238 moles. How many moles of HCl actually titrated with calcium carbonate? 0.00306 moles. Now that I've got the correct chemical in the correct reaction, then I can write the correct equation. HCl plus CaCO3, acid plus carbonate turns into salt plus water plus. This isn't acid plus regular base, this is acid plus carbonate turns into CO2. How do I balance this equation? Two on the HCl, good. So I've got a balanced equation. Reading the ratio in the equation that Curdy helped us balance, how am I going to get the moles of carbonate from my moles of HCl? I'm going to times it by 0.5. Half times my moles of HCl is half times 0.00306 moles. So how many moles of calcium carbonate do we have? 0.00153 moles. Now that I've got the chemical that they're after, then I can do whatever they want about that chemical. Same thing again, they want percentage of calcium carbonate. When you do percentages, you do it in the same unit. Percentage of calcium carbonate in the marble, what they told you about the marble is that it's a 0.188 gram. Percentages in the same unit. So if the marble is in grams, I need my calcium carbonate to be in grams as well. So mass of calcium carbonate in grams, moles times molar mass, 0.00153 moles times 40.08 or 09 for calcium, plus 12.01 plus 16 by 3 for oxygen. So what is my moles of mass of calcium carbonate? Oh yeah, that's right, 0.153 grams. As a percentage, weight on weight of calcium carbonate, it's going to be 0.153 grams over my entire sample, 0.188 times 100. (81.5%) rounded to 3 sig figs. Good. Okay, well done. All right, can I get a thumbs up, guys? Did this second one make a bit more sense? There's a little bit less to do with this one than the other one, yeah? All right, good work. Question 30, a 50 mils volume of 0.1 molar ethanoic acid solution is titrated against 0.1 molar NaOH. Calculate the pH in the conical flask. after 20 mils of NaOH is added. The Ka of ethanoic acid is 1.76 times 10 to the minus 5 at 25 degrees Celsius. So this looks like a titration question, but they're not asking you for concentration, they're asking you for pH. So they told you that titrating is just another word for mixing, because that's what happens in the conical flask. So this is basically a calculate the pH after you've mixed an acid with a base question,
Oh, okay, yeah.
which we have step by step for. And we did a question. Did we do a question? Question 25 was a mixing strong acid and strong base, which had its own working out. When you are mixing a weak acid or a weak base, though, the steps get a slightly bit more complicated.
Yeah.
Nonetheless, we can still do the steps. Step number 1 is to write a molecular equation for the acid and base. What's the formula for ethanoic acid?
Um, C2H 4O2.
Yes, I might do it the condensed way just so that we can see the acidic proton. So CH3COH aqueous. The formula for sodium hydroxide they've given you, NaOH.
Yeah.
And this is an acid plus base equation. Neutralization equations are always irreversible, so I use a single arrow. So I know ethanoic acid is weak, but I'm not in water. Otherwise, I'd do a double arrow. I'm reacting it with sodium hydroxide. So that's going to be a single arrow regular neutralization equation. Acid plus base turns into salt plus water. What salt do I make?
CH3COONA plus water.
Mm-hmm. Plus H2O. Step number 2, calculate the moles of each acid and each base added. So moles of CH3COOH added. They've given you concentration, they've given you volume. So I'm going to do C times V is 0.1 molar. And then the volume was 50 mils, so that's 0.050 liters, which is 0.005 moles.
Yeah.
I do the same thing for my base, NaOH, C times V. The concentration given to me in the question is also 0.1. And then the volume, they said they want me to figure out the pH after 20 mils of NaOH is added. So the volume is 20 mils. So that's going to be 0.020 liters, which is 0.002 moles.
Yeah.
Okay, step number 3, you want to figure out what your limiting and what your excess reagents are, because only the acid or the base that's in excess is going to affect the pH of your final solution. So number 3, limiting reagent check, you take the moles of each chemical and then you divide it by the coefficient in the equation, which means we would have had to balance the equation in the first place. But everything's a 1-to-1 ratio, so it actually already is balanced. So I take the moles, I divide it by the coefficient in the equation. Same thing for NaOH. And then when I'm checking for my limiting reagent, the chemical with the smaller number is going to be my limiting reagent. So 0.002 is less than 0.005. So therefore, NaOH is my limiting reagent, which means it gets completely used up, which means there's no excess base, there's excess acid. So when I go to calculate my final answer, I expect my final answer to have a pH less than 7 because that means there's acid left over. All of my base has been reacted.
Okay, yeah.
Once I figure out what's limiting and what's excess, number 4, I want to figure out the moles and concentration of the thing that's in excess. So moles of CH3COOH in excess is going to be the amount added minus the amount reacted.
Yeah.
The amount of CH3COH I added was figured out in step 2. That's the 0.005 mole. The amount reacted depends on my NaOH because that's the limiting reagent.
Yeah.
And it's a 1-to-1 ratio. So for each mole of NaOH added, for each mole of NaOH reacted, 1 mole of acetic acid reacts. So if I have 0.002 moles as my limiting reagent, that's the amount that reacted as well.
Okay, yeah.
So my moles of acetic acid that's left over, that's available to affect pH, is 0.003 mole.
Yeah.
Okay. Now, with a strong acid and a strong base, this is where you stop because if you have something strong, then the conjugate is really weak. And so something strong has a weaker conjugate, something weaker has a stronger conjugate. So if this was a strong acid, strong base calculation, you don't need to figure out the amount of the conjugate because it's not going to affect pH that much anyway.
Okay, yeah.
However, because this question has something weak inside of it, the conjugate is slightly stronger and it will affect your pH.
Okay.
So after step 4, if it was strong, you would go straight into figuring out how many protons or how many hydroxides is actually after, and then you sub it straight into your pH equation. But because it's weak, I'm not going to do that yet. I need the moles of the conjugate that's also produced as well. And the conjugate is found inside of your salt.
Okay, yeah.
So the moles of the CH3COH is a thing in excess. The conjugate of that is CH3COO minus. And CH3COO minus, I'm scanning my equation. I find it here.
Yeah.
It's a 1-to-1 ratio, so moles of acetate is equal to moles of sodium acetate. And sodium acetate is on the product side, so you don't have to figure out how much you added or how much you reacted. It wasn't added in the first place, it just got made. And how much gets made depends on how much limiting reagent you have. Once again, everything's a 1-to-1 ratio. So the moles of sodium acetate is the moles of NaOH, which is equal to the 0.002 moles you calculated earlier.
Okay, yeah.
And then when you were doing strong acid, strong base, after you figure out the amount of acid or base left over, you went straight into a chemical equation to figure out how many protons, how many hydroxides there were. With something weak, you don't use a single arrow, you use a double arrow, which means when you go to figure out the protons, you can't use the ratio like you do something strong. You have to set up an ice table.
Okay, yeah.
And your ice table takes concentration. So after you figure out the moles left over, we might turn this straight into concentration. Moles on volume is the 0.003 mole. Now at this point, you've already mixed your acid and your base together,
Yeah, okay,
which
yeah.
means your volume is not the volume that you had at the start anymore. It's going to be the total volume of the acid and base solutions that you've already mixed.
Okay, yeah.
So you had 50 mils and then 20 mils, which means by the time you've mixed it together, anything that gets made after that is going to be made in a total 50 mil solution,
Okay.
or in a total 70 mil solution.
Yeah.
So that's going to be 0.070 liters. So what's our concentration?
Um, 0.04, so on.
0.04 and so on. And then we do the same thing for the acetate ion because that goes into our salt as that goes into our ice table as well. So that's going to be N on V 0.002 mole divided by 0.070 liters.
And that's 0.02, so on.
0.02, so on. So now we have to figure out pH is a function of proton concentration, not the acid molecule concentration itself. So I need to know how much of that acid turns into the protons, which means I need to write a dissociation equation and set up an ice table.
Yeah.
So the base is not in excess, the acid is in excess. So CH3COOH, aqueous. plus H2OL turns into, oh, double arrow, CH3COO minus aqueous plus H3O plus aqueous.
Yeah.
Set up my ice table, ICE. My initial concentration of my acid, 0.04 and so on. And for my conjugate base is 0.02, so on. Normally when you do these equations, you have 0 for everything on the right, but it just so happens that we had a neutralization equation before this that made some of your acetate ion.
Okay, yeah.
So that's why it's not 0 anymore, but I haven't made any protons yet because the neutralization equation didn't make any protons, so that's still 0,
Yeah.
which means I'm still shifting to the right. So plus x minus x. So this is 0.04 with all of your decimals minus x. This is 0.02 with all of your decimals plus x, and this is x.
Yeah.
For me to solve for x, everything else after this goes back to what we're used to. Write your equilibrium expression, sub in your values, and solve for x. What's your equilibrium expression?
CH3COO minus and then H3O plus on CH3COOH.
Mm-hmm. And then I sub in my stuff, 0.02 with all of whatever those numbers are. So they need to be stored in your calculator plus x with another x over 0.04, all of those decimals minus x. They have to give you the Ka, otherwise this doesn't work. And they told you it's 1.76 times 10 to the minus 5.
Okay.
And then this is going to be a really ugly looking quadratic because there's x's added and subtracted with two numbers, not just one like we're used to. So I'm going to say Ka very small. So x is way smaller than whatever that 0.02 is, but also x is way smaller than whatever the 0.04 is.
Okay, yeah.
So this becomes approximately 0.02, whatever your decimals are, with x, and then 0.04. It's 1.76 times 10 to the minus 5. So for me to solve for this, I need to multiply that number starting with 0.04 and then divide that number starting with 0.02.
Yeah.
So x is 1.76 times 10 to the minus 5 multiplied by 0.04 dot 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 divided by 0.02 dot dot dot, and then x is equal to
2.64 times 10 to the minus 5.
times 10 to the minus 5 molar. And then from your ice table, X is the H3O plus. So let's see, are they asking me for pH or POH? They're asking me for pH, which means I've got the correct ion. I've got the H plus ion. So I sub this straight into the pH formula. If they were asking me for POH, I would still have to sub it into the pH formula and then convert it to POH after.
Okay, yeah.
So pH is negative log base 10, H3O plus, which from our ice table, we said that that's negative log base 10 of x. So negative log base 10, 2.64 times 10 to the minus 5. And what is pH?
4.5.
4.5, which is less than 7, like we expected, because we had excess acid. And then we want to round this off to 2 sig figs correctly.
Okay.
Question 31. Explain why a potassium hydrogen sulfite, HSO3, produces an acidic solution in water, while potassium hydrogen carbonate, HCO3 minus, produces a basic solution in water. Support your answer with relevant chemical equations. So this is similar to the previous question. Question 19, where they were asking us, oh, why is the pH of ammonia greater than 7, which means it's basic? And we said it's because it takes protons from water to produce a hydroxide. So it kind of seems like in this case, oh, if KHSO3 is acidic, it gives protons to water. And if KHCO3 is basic, it takes protons from water, which seems
Yeah.
like it's not going to be worth that many marks, but this is a 5-mark question. So I feel like there has to be a little bit more detail that we talk about here. And hopefully what you recognize is the hydrogen sulfide. So if K is K plus, then hydrogen sulfide is HSO3 minus.
Yeah.
And then likewise, if potassium is K plus, then HCO3 is HCO3 minus.
Yeah.
And then when you look at the formula, they each have a proton, which means they can both give away protons to water. So then it
Yeah.
makes sense that HSO3 is acidic. It gives away protons, it turns into a H0 plus. But then that doesn't explain why HCO3 is basic. But the hydrogen means that it can give away protons, and the minus charge means that it's attracted to a H plus, because opposite charges attract, which means the complication here is what they're basically asking you is how come HSO3 is acidic and HCO3 is basic when they are both amphiprotic, when they're both capable of being acids as well as bases.
Okay. Yeah.
So your answer to this question is going to be, even though it's amphiprotic, it prefers to do one thing over the other.
Yeah.
So that's part of the 5 marks, acknowledging that it's amphiprotic in the first place, which is why they can ask a question like this.
Okay. Yeah.
So we might start there. We might say, oh, um, the anion, because when we go to write our equation, it's not in terms of the potassium. We singled out the HSO3 and the HCO3. So before I even go into my answer, I need to lay out a picture for the marker. The anion in KHSO3 is HSO3 minus,
Yeah.
and the anion in KCO3, oh, KHCO3 is HCO3 minus.
Yeah.
They each have a H plus that can be donated and a minus charge, which is attracted to a H plus.
Yeah.
So therefore, they can act as both Bl acid plus Bl base, which means that they're technically amphiprotic. So this is a 5-mark question. We want to add a bit more detail. And the reason it's relevant is because we because there are both options, because it's both acidic and basic, we need to set up that picture because we need to explain the marker why later on we choose one to be a bit more acidic and we choose the other one to be a bit more basic.
Yeah.
Okay, so they're both amphiprotic, but what we might say is HSO3 minus is a if it's an acidic solution, what that means is it prefers to be an acid over being a base. So HSO3 minus is a stronger acid than water, but it's a weaker base than water, which means it prefers to be an acid and it would rather let water be the base.
Okay. Yeah.
So what that means is in aqueous solution, it would rather take a proton, oh sorry, it would rather give a proton and therefore produce an acidic solution, and then you can write the equation here.
Okay. Yeah.
And then likewise, the reason why HCO3 minus is basic in water is even though it can do both, water must be, if it's basic in water, what that means is water must be more acidic than it. Because if water is more acidic, then it'll be the base.
Yeah.
So HCO3 minus is a stronger base than H2O, and then likewise, it's going to be a weaker acid. So that'll leave water to be the acid. So if it's a stronger base, then in aqueous solution, it prefers to take a proton. And then when you go to write the equation for H03 minus, you'll actually end up with OH minus on the right-hand side. 32, the pH of blood is maintained by a buffer solution containing carbonic acid and hydrogen carbonate. Explain the effect on blood of an elevated concentration of carbon dioxide. Include a relevant equation in your answer. So this is straight from actually, no, not really. It's a little bit of a different worded question. So explain the effect on blood of an elevated concentration of carbon dioxide. This is actually not straight from your syllabus. A straight from your syllabus question would be like, just explain how a regular buffer works. This one's slightly different. So let's have a look. This is a buffer question. Now, just keep in mind that a buffer resists changes in pH. So we always want to, certain definitions that are very clear cut, you want to always include that in. This is a double arrow, so this is an equilibrium concentration question. And then the only issue is, though, an elevated concentration of carbon dioxide. And then you're like, okay, so if at a normal LCP theory, if the concentration of CO2 goes up, then the position of equilibrium will shift to the other way to try to bring the concentration of CO2 back down. But then it's like, there's no CO2 in this equation.
Yeah.
So maybe that's where the total 4 marks comes from. Because otherwise it would just be a regular LCP question. Concentration of CO2 goes up, shift it the other way, bring it back down. That would just be at most 2 marks. So maybe that explains why this is a lot more marks than we're used to. Now, hopefully what we remember from the beginning of module 6 is that metal oxides are basic and non-metal oxides are acidic. So carbon dioxide is not in this equation. However, when you dissolve CO2 gas in water, it produces carbonic acid.
Yeah.
So what they mean by, oh, increased concentration of CO2 is that if this goes up, is it a double arrow or a single arrow? I think it might just be a single arrow. So if the concentration of CO2 goes up, then this reaction occurs and the concentration of H2CO3 goes up.
Yeah.
And then H2CO3 is present in your equation. So this goes up.
All right. Okay.
And the position of equilibrium will shift to the other way to try to bring the concentration of H2CO3 back down.
Okay. Yeah.
So now, that's where the few bits of extra marks come from. And then the hint in this question actually is the fact that they asked you to include an equation in your answer. So that's sort of the hint here. They've already given you an equation. So if you were to face this question in your exam, it would be like, why is the question asking me to include an equation when they've already given me one? And that's sort of the light bulb moment in your head where it's like, okay, there has to be another equation somewhere. And maybe that explains why carbon dioxide's not in this equation that they've given me. There has to be another equation.
Okay. Yeah.
So CO2 is non-metal gas. Sorry, is a non-metal oxides. Non-metal oxides are acidic. When it dissolves in water, it makes H2CO3, and this is where your equation comes in.
Yeah.
So then if the concentration of CO2 is higher, then the reaction occurs and the concentration of H2CO3 is also higher.
Yeah.
And then this is where you can start applying LCP. So maybe bring in your definition of LCP somewhere here. Normally we bring the definition of LCP at the start, and that's because with regular Module 5 questions, everything in your answer relates to LCP. But this first half of the answer, where you were setting up the picture about why CO2 is even relevant, didn't need LCP. So I might bring in the definition of LCP here. When a system is at equilibrium and it experiences a disturbance, the position of equilibrium will shift the opposite way to counteract the change.
Yeah.
So then if the concentration of H2CO3 goes up, then according to LCP, the position of equilibrium will
Um,
shift
to the right,
to the right to try to,
minimize the increase in concentration.
yeah, to try to bring this back down and counteract the change. And as a result of that, instead of you make less H2CO3 and you make more of the HCO3 minus and the H3O plus on the right.
Yeah.
And therefore, link this to your definition of the buffer. You effectively counteract the change in pH. I'll say delta pH. Please don't write like this in your exam. Effectively counteract the change in pH caused by the CO2.
Okay, yeah.
All right, so let's say like the effect on the actual blood is probably this section. Explain questions are normally 2 marks. So then the explanation about the actual LCP, that will be where your 2 marks comes from. And then 1 mark comes from your equation, but then it's a 4 mark question. So the extra mark has to come from linking CO2 to that LCP stuff in the first place. So making the CO2 relevant, the fact that it produces H2CO3 will be your 4th mark.
Okay, yeah.
Any questions?
No.
Okay, good. So anytime you don't see a relevant chemical, but they've given you another equation, there has to be something that's going on. So in module 5, if you get a chemical equation and then they tell you, oh, you're adding something to it, but that thing is not in the actual equation, it's normally a precipitation reaction.
Yeah.
Where, like, if you add silver nitrate, it precipitates out the chloride and then you decrease the concentration of the chloride and then it goes back to try to make more of it, things like that. You don't see that here because module 6 isn't about precipitation. But usually, if you see a chemical get mentioned that's not in the equation, it's normally precipitation if it's module 5. But now you know that in module 6, you can also get some other things.
Okay, yeah.
Keep in mind this is true for the other polyatomic acids. So like CO2 plus H2O turns into your H2CO3. And then if it's like, if you have SO3, sulfur trioxide, and with H2O, that makes your H2SO4.
Okay, yeah.
Yeah, so just keep these equations in your pocket just in case you get a similar, as you apply it in a similar case. And then also another one, nitrogen dioxide plus H2O turns into your nitric acid.
Okay, yeah.
And then that's about it. And then if you turn this into SO2 instead of SO3, then you'll make H2SO3, which is sulfurous acid.
Yeah.
And then also like nitrogen monoxide plus H2O turns into HNO2, which we saw in like 1 or 2 of the previous questions. That's a weak acid.
Yeah.
Okay, so keep these equations in your pocket just in case you get something similar to it.
Okay, yeah.
Last question in the Module 6 HSC prep doc. Explain the difference in the changes in pH when 3 drops of 1 molar HCl is added to distilled water and to an equimolar mixture of carbonic acid and bicarbonate ions. Okay, now, if there are changes in pH, they must respond to it in different ways somehow. So hopefully we're able to identify at this point that when you have an equimolar mixture of something, your best guess is that it's going to end up being a buffer. Watch out though, it's possible that NASA plays with you and they give you an equimolar mixture of a strong acid and its conjugate base, which would not form a buffer.
Okay, yeah.
For a buffer, you need a weak acid and its conjugate base. But normally, safe assumption is that it just works out as a buffer.
Okay, yeah.
So 4 mark question, two explanations, adding HCl in water and adding HCl in carbonic acid. So two explanations each, 2 marks for the distilled water part, 2 marks for the buffer part. So we have to talk about what the changes in pH are. Distilled water does nothing. Distilled water is what we usually add stuff to. So you talk about the distilled water part the way you normally talk about things.
Okay.
So sometimes students see questions and they're like, I don't know what to do when something like this comes up. It's not because you don't know what to do, it's just because you haven't like focused on it because it's how you normally do things. So you might see like you might see this question and then think, I don't know what HCl does in water. You always know what HCl does in water because that's the main thing that we study.
Okay, yeah.
So just keep that in mind moving forward. In water is how you normally do things. So is oh, HCl is a bronzolaric acid. It donates a proton to H2O, therefore it makes H3O plus, which means it becomes more acidic. And if it becomes more acidic, what's happening to pH?
It's decreasing.
Yeah, pH is decreasing. Now we can make this a bit more specific. You don't, actually you could. You could calculate what's the pH at the start if it's water.
7.
pH of 7, and then could you calculate the pH when you add the HCl?
Yeah.
Yeah, you could. And then you could calculate pH is negative log base 10 of H plus, and then sub in the 1 mole of a HCl. So you can make your answer really, really specific.
Okay, yeah.
And then in here, we'd probably include the acid dissociation equation.
Yeah.
So HCl plus H2O, single arrow turns into Cl minus. So we can make this more specific. That would really get you some ticks in your answer. So that's the 2 marks. And then your second 2 marks comes from carbonic acid. For us to talk about it resisting the change in pH, we have to tell the marker that it's a buffer in the first place. And then for it to be a buffer, it has to be a weak acid and base. So we have to set up that picture first. So let's go carbonic acid is a weak acid, and then bicarbonate is the conjugate base. So if it's an equimolar mixture, then it forms a buffer.
Yeah.
And then you include your equation here. What's your equation? H2CO3 plus H2O, double arrow because it's weak, turns into HCO3 minus plus H2O. The buffer part of this answer is going to take a little bit more to do because it's resisting the change in pH, which means it's going back and forth, which means we have to talk about LCP.
Yeah.
So when you add drops of HCl, it's gonna H3O plus, it's gonna HCl is an acid, so it donates protons. We already talked about that earlier. So if you already mentioned this part, we don't really have to say, oh, it's an acid, it donates protons again. You can skip over that and go straight into, if you add drops of HCl, you're gonna increase the concentration of H3O plus.
Okay, yeah.
And then if you do this temporarily, just like it did in water, the pH is going to decrease.
Yeah.
But it can't stay there because that's what you talked about with the water. Otherwise, this wouldn't be a 4 mark question. So what happens after you add the H0 plus? According to LCP, the position of equilibrium shifts to the left to try to counteract it, which means over time, what happens to the same concentration of H3O plus?
It decreases.
It goes back down. And therefore, what happens to pH if the H3O plus concentration goes back down?
It increases.
It increases. So pH went down at the start, then pH went back up. So therefore, what do we say? The buffer resisted a change in pH.